So this is a series of lecture to understand Higgs mechanism and how weak nuclear gauge bosons W plus minus W minus and Z naught gains mass. But before we start with Higgs mechanism, we have to have some knowledge of Lagrangian dynamics. Motion of a particle can be solved more easily by method of Lagrangian than by Newtonian method because it involves energy and not force, hence constraint force have no chance to creep in. Also, Lagrangian has embedded in it all the conservation laws. Symmetry of the Lagrangian dictates what is conserved and what is not. So, the Lagrangian function is a difference. So, we are starting with the Lagrangian dynamics because it's we require Lagrangian dynamics to understand Higgs mechanisms. So, the Lagrangian function classically the Lagrangian function is a difference of kinetic energy and potential energy, kinetic energy and potential energy. And the Lagrangian function L is difference of kinetic energy and potential energy. As the particle moves, both the kinetic energy and potential energy varies, as such the Lagrangian varies. So according to Hamilton's principle, if you divide the whole duration of motion into small time segments, time elements, say delta t, whole duration of motion, suppose starting time is t1 and end time is t2, and the particle moves along the path as shown from time t1 to t2. If you divide the whole duration into small time elements and multiply it by corresponding Lagrangian, means the difference of kinetic energy and potential energy, that L1 is the Lagrangian during the small duration delta t. So this is the multiplication of Lagrangian, corresponding Lagrangian with the time, and this is called action. So according to Hamilton's principle, the whole sum of the whole action from time t1 to t2, if you sum over the whole Lagrangian, whole action, so it's next Lagrangian is delta 2 and next delta 3 and so on. If you sum up over the whole Lagrangian and assuming that delta t is so small that in that small time Lagrangian remains constant, so this can be written as limit delta t tends towards 0. So this is the whole action, and this is action, let us denote it by S. This is action. This can also be written as integration from time t1 to time t2 L. So according to Hamilton's principle, this must be constant, means any variation in the action must be 0 with no any variation. This will not be, it means the path followed by the particle will always be the extrema. So this is all about, this is Hamilton's principle. Okay. So we will derive equation of motion from this principle. So our Hamilton's is we are deriving equation of motion from Hamilton's principle. Hamilton's. So our Hamilton's principle is delta S, which is wedge L dt and T1 to T2 must be 0. Now we know that the Lagrangian is a difference of kinetic energy and potential energy. It means Lagrangian is a function of generalized coordinates, generalized velocity and time. So it means Lagrangian is a function of generalized coordinate I. I is the index, Q denotes the generalized coordinates, and the number of generalized coordinates I is maybe 1, 2, 3, 4, and Q dot generalized velocity, and it also depends on time then. Now, it means this can also be written as delta L T1 T2. So our aim is to find this. So delta L means variation in the Lagrangian. Now since the Lagrangian depends on both on generalized coordinates, generalized velocity and time. So any variation in Lagrangian means the variation of Lagrangian with respect to the generalized coordinate and the variation in the generalized coordinate plus variation in the Lagrangian with respect to the generalized velocities and the variation in the generalized velocities. Now, as I am assuming here that the Lagrangian does not depend explicitly on time, so I am not taking the time component here. Okay. Now, here, so it will be, substitute the values of delta L here, this will become delta L by delta Qi, delta Qi time T1 to time T2 plus T1 to T2 delta L by delta Qi dot delta Qi dot dt, and this must be 0. Okay. Now we'll integrate this one. Let us call it as number 1. Now integrate this part. So if you integrate this one, delta L by delta Qi dot delta Qi dot dt T1 to this will be integrated first, so it will be delta L by delta Qi dot. Integration of this means removal of dot because you are integrating with respect to time. So it will be delta Qi time T1 to limit time T1 to T2 minus under the integral differential of this one. So d by dt delta L by and integration of this. Now, since at the end times there is no variation in the generalized coordinates, because at the end times, they meet all the they meet at the end times. So there is no variation in the generalized coordinates at time t1 and time t2. So this means at the end times, the value of delta q I at time t1 will be 0, and also of that of q time t2 will be 0. It means this part will be 0. So you are left with, our integration is left with, this part. We substitute for this integral this value here in equation 1. Substituting in equation 1, we get what we get. Substitute here, this will remain as it is, t1 to t2 delta L by delta qi dt. Now for this, we have this value with negative sign here, so the negative sign comes here, and time t1 to t2 d by dt delta L by delta qi dot delta qi, and this whole thing must be 0. Okay, it's all right up to now. It's not. So I'm removing this, using this can be written as t1 to t2 delta L by delta qi minus d by dt delta L by delta qi dot and delta qi. Now for holonomic constraints, these generalized variation in generalized coordinates are independent of each other. Holonomic generalized coordinates are independent and arbitrary. So for this integration to be 0, this integrand part must be 0. So it means this must be 0, means delta L by delta qi minus d by dt delta L by delta qi dot is 0. So this is our equation, final equation of motion, and this is called Lagrange's equation of motion. Okay. Now we will do a simple problem. Simple problem for one-dimensional motion. For example, consider the motion of a particle attached to a spring of say spring constant K, and the motion is obviously one dimensional because we are taking spring constant is K. Suppose mass is M. So I am taking the simple example of a mass attached to a spring of spring constant K and moving along the x-axis. So we have the Lagrange's equation of motion. This is our equation of motion, where qi is the generalized coordinate. I is an index denoting the degrees of freedom. Now here we are only having 1 degree of freedom, and the generalized coordinate is simply x. So q is only 1, and this denotes x, and q dot denotes x dot. Now the Lagrangian here is the difference of kinetic energy and potential energy. So Lagrangian is kinetic energy minus potential energy, and kinetic energy is half m x dot square, and the potential energy is half k x square. This we know that the potential energy attached to a spring constant K is. Now we have to find this. So it is del by del x, del by. We get minus k x. Differentiate this one, 2 will cancel out. And delta L by delta x dot. So this m x dot. Now next is d by dt of delta L by delta x dot. So it will m x double dot. This Newton's, in the Newton's law, this is the force, and this is the momentum, x component of the momentum. Now substitute the values in this motion. Get m x double dot minus, but there is a minus here, kx is equal to 0, and mx double dot is equal to minus kx. This is a well-known equation of simple harmonic motion. The equation of motion here denotes that this motion will be a simple harmonic. So this is a simple harmonic motion, and the time period motion will be given by the time period will, and x dot will be minus k by m x the acceleration is proportional to displacement with the negative sign, and this is the constant. Acceleration is proportional to displacement with the negatives. This is the criteria for simple harmonic motion. In the time period, T is given by 2 pi under root of constant and the constant here is k by m. So it is 2 pi under root k by m or 2 pi m by k. Okay. So here we have, in the case of spring motion, we have found that the potential energy B is half k x squared. Means the potential energy varies as the square of the displacement. If you plot a graph of the variation of potential energy with displacement from the mean, you will get graph something like parabolic graph, just like so. So this was all about Lagrange's equation of motion, which is the basic equation here, and one of the I have solved one of the problems related to and showed you how the potential energy varies with the displacement. So the next class we will discuss Lagrange for continuous body. Here we have worked out for discrete particles, but for continuous system. That will lead you to the Lagrange for fields. So for today it's alright. For the next class we will discuss Lagrange for continuous systems.